Hi everyone, this is Kalyan Kumar and welcome to Chemistry Tutorials, your one-stop channel for a variety of chemistry videos covering all parts of chemistry, physical, organic and inorganic. We are currently doing the lesson General Organic Chemistry and I've already made 3 videos on that, Part 1, Part 2 and Part 3a. Now Part 1 was about the introduction to hybridization of carbon atoms as well as inductive effect. Part 2 was about resonance effect. And Part 3 was supposed to be aromaticity, but as I was making the content, developing the content, I realized that aromaticity is something so huge that requires several parts in itself. Earlier I thought I'll just make 2 parts, 3a and 3b, but when I was working on the video of 3a, which was about an hour and 13 minutes, it took me almost 30 hours to render that video. And I realized that that way I would not be able to post at least 2 videos, which is what I want per week, which I could not do so last week because of this issue. 30 hours, more than one day to render one video, which is 1 hour and 13 minutes. So I decided to make shorter videos. So I decided that aromaticity will be covered in 4 parts. A part I've already done, which was about the conditions that are required for a molecule to qualify as aromatic, anti-aromatic or non-aromatic. Second part, 3b, which is this one, is going to cover the introduction to molecular orbital theory for pi bonds. Because ultimately this particular aromaticity, this second part of aromaticity, after learning how to identify a molecule, whether it is aromatic or not, the second part covers the molecular orbital theory approach, which explains the need for 4n plus 2 and 4n pi electrons for a molecule to be aromatic or anti-aromatic respectively. So to cover the molecular orbital theory, I am making that into 3 sections, 3b, 3c and 3d. 3b, which is this part, again as I said, I am going to talk about the molecular orbital theory of pi bonds. So first I'll start with the simplest sigma bond, that is the hydrogen molecule. Then we will move to pi bonds. And then we'll move to conjugated pi bonds where resonance is shown. That is what we're going to cover in this particular video. So let's get the show on the road. And this is part 3b of 13, Introduction to Molecular Orbital Theory for Pi Bonds. So we are going to do the molecular orbital theory first of all for sigma bonds to understand the basic idea about how this theory works. Now, valence bond theory does a remarkably good job at explaining the bonding geometry of many of the functional groups in organic compounds. There are some areas, however, where the valence bond theory falls short. Valence bond theory is all about locating the electron. It was treating the electron like a particle. We said electron is here, then it moved here, and then improvements were done in the valence bond theory to include the wave nature to a little extent by talking about orbitals. Again, we used to place electrons in boxes, though we termed orbital as the region of space where the probability, the moment we hit a probability, it's talking about the wave nature of electrons. But we still used to place the electron in boxes, upward arrow and downward arrow. But what happens is that there is a limitation beyond which the valence bond theory doesn't work. It can predict the shape of molecules, the structure of molecules to some extent, but it cannot explain all the properties of a molecule. The fact that bonds can be fractional is not explained by valence bond theory, and that is why we invoked to bridge the gap of what the valence bond theory says and what reality is. We use what is known as the resonance effect. But the fact of the matter is, actually one needs to use the molecular orbital theory. Resonance is only a bypass to take care of the complicated form of the molecular orbital theory. It fails to adequately account, for example, some interesting properties of compounds that contain alternating double and single bonds. That is where the resonance occurs. In order to understand these properties, we need to think about chemical bonding in a new way, using the ideas of molecular orbital or MO theory. So let's go back and consider the simplest molecule, the covalent bond in hydrogen molecule. Now when we described the hydrogen molecule using valence bond theory, We said that the two 1s orbital from each atom overlap, allowing the two electrons to be shared and thus forming a covalent bond. Whereas in the molecular orbital theory, we make a further statement. We say that the two atomic 1s orbitals mathematically combine to form two new orbitals. Now, what we are basically primarily trying to say here is that the molecular orbital theory assumes electron like a wave, and it assumes that when the two electrons interact in forming a bond, basically the waves superimpose. And if you are a beginner, you might not know, if you're in grade 11, you might not know what is the phenomenon of interference. Interference is the combination of two waves, and the two waves can combine constructively or destructively. When they combine constructively, then the mountain of one wave and the mountain of the other wave, they are aligned, and otherwise the mountain of one wave will be aligned with the valley of the other, which would mean that it is a destructive interference. Now, recall that an atomic orbital such as the 1s orbital of hydrogen atom describes a region of space around a single atom inside which electrons are likely to be found. A molecular orbital, in fact, does the same thing for a molecule. What it says is that for a given molecule, a molecular orbital represents the region of space where there is a high probability of finding the electron between the two atoms, forming that particular bond. A molecular orbital describes a region of space around two or more atoms inside which electrons are likely to be found. Now, mathematical principles tell us that when orbitals combine, the number of orbitals before the combination takes place must be equal to the number of new orbitals that result from the combination. Orbitals just don't disappear. When two atomic 1s orbitals combine in the formation of H2, the result is two sigma orbitals. As I mentioned, the waves of the two electrons can meet each other constructively or destructively. The constructive is called the bonding molecular orbital, and the destructive is called the anti-bonding molecular orbital. So this is the situation. Energy, we got the first box, single electron, 1s orbital of hydrogen. Another molecule, another atom, which has again a 1s orbital. These are atomic orbitals, and they are going to combine to form molecular orbitals, and the electrons are found here because this is lower in energy than the two atomic orbitals. If you notice here, these are the two atomic orbitals. These are the two atomic orbitals, and this is the molecular orbital that results from them, and this is the level of the energy of atomic orbital, because remember, this axis is energy axis. This is lower in energy, so the electrons are found here. And in this case, you will notice that these circles, they are the nucleus. So this is also the nucleus of the other atom. And you will notice that this region is broader. That means there is a high probability of finding the electron in between the two nuclei, and it is very narrow near the nucleus, which implies there is a very low probability of finding the electron near the nucleus, which is what bonding is all about. Whereas if you look at the other one, this is called sigma bonding. If you look at the other one, this is the destructive interference, and here the molecular orbitals look like this. The broader region is near the nucleus, near the two independent nuclei, and in between them there is hardly, exactly in the middle, if you look at it, exactly in the middle you will find this part, there is hardly any electron, there is no electron. So right between the atoms there is no electron, so this is known as the anti-bonding molecular orbital or sigma star. And this part is known as the nodal plane, the place where the electron's density is very, very low or almost zero. So according to the MO theory, one sigma orbital is lower in energy than either of the two isolated atomic 1s orbitals. This lower sigma orbital is referred to as bonding molecular orbital. The second sigma star orbital is higher in energy than the two atomic 1s orbitals and is referred to as anti-bonding molecular orbital. Now the bonding sigma orbital, which holds both electrons in the ground state of the molecule, is egg-shaped, encompassing the two nuclei with the highest likelihood of electrons being in the area between the two nuclei. Whereas the high energy antibonding sigma star orbital can be visualized as a pair of droplets with areas of high electron density near each nucleus and a node, that is the area of zero electron density, midway between the two nuclei. And remember that we are talking about an electron here like a wave. And when two separate waves combine, they can do so with constructive interference, where the two amplitudes build up and reinforce one another, or destructive interference, where the two amplitudes cancel one another. So when the crest of one wave meets the trough of the other wave, it cancels out. When the crest and the crest meet and the trough meet, it is a constructive interference. Now remember one thing, that a wave has an amplitude in both the positive x and the negative x direction. The negative x direction has no particular significance in terms of negative. It doesn't mean the electron density is not there. Basically, we wanted to name one as positive and the other as negative, but this has got nothing to do with the presence or absence of an electron. It is as much likely to find an electron in the crest as much as it is in the trough. So we just wanted to name the crest and the trough in a particular way, that particular direction. So we named it as plus and minus. We could have named in any other possible way. So basically, the plus and the minus does not signify anything. It is just that we distinguish both by using the symbols plus and minus. So bonding MOs are the consequence of constructive interference between the two atomic orbitals, which results in an attractive interaction and an increase in electron density between the nuclei. Antibonding MOs, on the other hand, are the consequence of destructive interference, which results in a repulsive interaction and a region of zero electron density between the two nuclei. Now, if you remember, we used to follow the Fball principle in filling the electrons in the atomic orbitals when you did the electronic configuration. Fball in German basically means building up. Contrary to what many people believe, Fball is not the name of any scientist. It is a German word for building up. So if you use the Fball principle, building up, it tells you that you must fill the lower energy orbitals first completely before you go for the higher ones. So following the same Fball principle, building up principle, you learned in chemical bonding, for writing out electronic configurations, we place the two electrons in the H2 molecule in the lowest energy molecular orbital, which is the bonding sigma orbital. The bonding, which is also the attracting MO, is full, and the antibonding, which is repelling MO, is empty. So now let's look for a pi bond. We'll start with the simplest one, ethene. Now the advantage of using MO theory to understand organic molecules becomes more apparent when we think about pi bonds. Let's first consider the pi bond of ethene from an MO theory standpoint. In this example, we will be disregarding the sigma bonds in the molecule and thinking only about the pi bond. So whatever diagrams I'm going to show you is only meant for pi bonds. Sigma bonds I'm not showing does not mean they're not there. I'm just showing the MO theory for pi bonds. We start with two atomic orbitals, one unhybridized 2p orbital from each carbon atom, which contains a single electron. In MO theory, the two atomic combine mathematically to form two pi molecular orbitals, one a low energy pi bonding and one a high energy pi star antibonding. So this is how they look like. This is the energy axis. This is atomic orbital. Blue and red, they signify the different signs of the wave. Again, as I said, there is no significance of these. Blue and red are equivalent. This is the second atomic orbital. I am talking about ethene. So there are two carbon atoms. They've already formed a sigma bond and we are talking about the pi bond. So they interfere. This is the energy of the atomic orbital. They interfere and give rise to two molecular orbitals. Remember, the number of molecular orbitals will always be equal to the number of atomic orbitals from which they are formed. And here you have the two electrons placed because the lower energy than atomic orbitals. This is called the bonding. And as you can see, the blue and the blue bond and the red in the bond, and this is the constructive interference. The crest of one and the crest of the other, they are meeting together. The trough of one and the trough of the other, they are meeting together. This is called bonding, constructive interference. And this is called pi bonding MO, written as pi. And they can also meet destructively. Blue meets with red blue meets with red and red meets with blue, it's destructive interference. It's called pi antibonding MO pi star, and this is the nodal plane or the nodal point, you can call it. Now in the bonding pi orbital, the two blue lobes of the p orbitals interact constructively with each other, as do the two red lobes. Remember, the arbitrary coloring choice represents plus and minus signs for the mathematical wave function describing the orbital. There is increased electron density between the two carbon nuclei in the molecular orbital. It is a bonding interaction. In the higher energy antibonding pi star orbital, the blue lobe of one p orbital interacts destructively with the red lobe of the second, leading to a node between the two atoms and overall repulsion between the two carbon atoms. Again, using the building up principle, we place the two electrons in the lower energy bonding pi molecular orbital. The antibonding pi star orbital remains empty. Now that we have seen for pi bond, let's look at a situation where you have a conjugated pi bond. We are going to look at 1,3-butadiene. So the next one is the molecular orbital theory of pi bonds for 1,3-butadiene. This is where resonance occurs, remember. So we are going to see how resonance is explained by molecular orbital theory. This is the molecule 1,3-butadiene. This is the numbering. You can either number it left to right or right to left. It's a symmetrical molecule. Now from valence bond theory alone, we would predict that the bond between 1 and 2 is perfectly double, and the bond between carbon 2 and carbon 3 is perfectly single. And if you remember the first video when we talked about hybridization of carbon atoms, we said that when carbon is having a sigma bond and no pi bond, a single bond, rotation is free. So we should expect that C2-C3 bond should be easy to rotate because it's a single bond. From valence bond theory alone, we might expect the C2-C3 bond in this molecule being sigma bond would be easy to rotate. But experimentally, we find something else. However, it is observed that there is a significant barrier to rotation about the C2-C3 bond, and the entire molecule is planar. In addition, the C2-C3 bond is 148 picometer long, shorter than a typical carbon-carbon single bond, which is 154 picometers, though longer than the typical double bond, which is 134 picometers. What you should also understand in these values is that it is not exactly in the middle. It's not the average of the two. It is smaller than a sigma bond, a single bond, and longer than a double bond. How much is it single and it is double, we can always find out mathematically once we know the value of the actual bond radius and the radius of the bond length of sigma and a single bond and a double bond. But the idea is that it's not exactly or necessarily exactly in the middle. Molecular orbital theory accounts for these observations with the concept of delocalized pi bonds. Now in this picture, the 4 2p atomic orbitals will combine mathematically to form 4 pi molecular orbitals of increasing energy. 2 of these, the bonding pi orbitals, are lower in energy than the p atomic orbitals from which they are formed, while 2, the antibonding pi star orbitals, are higher in energy. Now in this case, what happens is, molecular orbital theory rightly predicts that there is some kind of a bonding interaction between carbon 1, 2 as well as 2, 3 and 3, 4. Now valence bond theory already talked about pi bond of 1 and 2 and 3 and 4, but it never talks about the pi bond of 2 and 3. But molecular orbital theory predicts that there is some kind of interaction between 2 and 3 carbon as well in terms of a pi bond, which is what is explained by resonance. Now in the diagram that I am about to show you, please understand the gap of the energy levels are not the actual representation of actual energy, because actual energies will have some value which in fact we need to find out mathematically. But the idea is that these are symbolic gaps. The gaps do not reflect the actual gap. So if you find one gap larger than the other, it doesn't really mean that in reality it is larger than the other. It is just drawn not to scale. So energy, there are 4 atomic orbitals now. Remember, 4 electrons of 4 pi electrons of the 4 carbon atoms. These are the atomic orbitals, and this is the energy of the atomic orbitals, and they interfere with each other, gives you psi 1, which is called the bonding molecular interaction. Now here you will notice that this is a bonding interaction. Blue meets blue, bonding. Blue meets blue, bonding. Blue meets blue, bonding. Obviously, when blue meets blue, red will meet red. So, there is one bonding interaction. Blue meet and red meet is called one bonding interaction. Don't take it as two. So, one bonding, two bonding, and three bonding. So, there are three bonding interactions, and there are no anti-bonding interactions here. So, there are no nodes. Nodes, you can assume, are the points where destructive interference occurs. So, 0 nodes, 3 bonding interactions, 0 anti-bonding interactions. It's called bonding MO. What you also need to understand is, how do we decide whether something is bonding or anti-bonding? Or sometimes you will also get into non-bonding. If the number of bonding interactions is greater than the anti-bonding interactions, it is a bonding molecular orbital. If the number of bonding interactions is equal to the number of anti-bonding interactions, it is non-bonding molecular orbital. And if obviously the destructive interference is greater, that means the places where they do not meet correctly, so where there is nodal points more than the bonding interactions, or anti-bonding interactions are greater than bonding interactions, it is known as an anti-bonding molecular orbital. So this is the second molecular orbital, psi2. This is the wave function, and as you notice, there is one bonding interaction here, there is one bonding interaction here, but this is the anti-bonding interaction. So, two bonding interactions and one anti-bonding interaction. It has got one node. So, one node, two bonding interactions and one anti-bonding interaction. Since bonding interactions are still greater, it is called bonding MO. Next, you have the one which is higher in energy than the atomic orbitals, psi3 star, and look at this one. There is one bonding interaction here, there is one anti-bonding here and one anti-bonding interaction here. So, two anti-bonding interactions and one bonding interaction, making it an anti-bonding molecular orbital. Two nodes. So, two nodes, one bonding interaction, two anti-bonding interaction, it's anti-bonding MO. And then you have psi4 star, which has only anti-bonding interactions. There are no bonding interactions, as you can see. One node here, second node here, and third node here. So, 3 nodes, 0 bonding interactions and 3 anti-bonding interactions. It is the highest energy anti-bonding molecular orbital. Now, where are the electrons? The electrons are in psi1, because according to the Fball principle, fill the lower one first, then psi2, and there are only 4 electrons, so the electrons get filled up in psi1 and psi2. And as you notice here, in psi1, which is the lowest in energy, there is some interaction between carbon 2 and carbon 3 as well, which is not revealed by the valence bond theory. Now, this particular orbital, which is the highest in energy where filling takes place, is called a HOMO molecular orbital, or a highest occupied molecular orbital. This one is called LUMO, the lowest unoccupied molecular orbital. So, among all the molecular orbitals, the one which is highest in energy and filled is this. The one which is lowest in energy and empty is this. So, psi2 is the highest occupied molecular orbital, called the HOMO, and psi3 star is the lowest unoccupied molecular orbital, called the LUMO. And we'll understand the use of these terms later on. So, let's describe what we saw. The lowest energy molecular orbital, psi1, has only constructive interaction and 0 nodes. Higher in energy but still lower than that isolated p orbital is psi2 orbital, which has 1 node but 2 constructive interactions. Thus, it is still a bonding orbital overall. Looking at the 2 anti-bonding orbitals, psi3 star has 2 nodes and 1 constructive interaction, while psi4 star has 3 nodes and 0 constructive interaction. And by the Fball principle, the 4 electrons from the isolated 2pz atomic orbitals are placed in the bonding psi1 and psi2 only. And because psi1 includes constructive interaction between C2 and C3, there is a degree in 1,3-butadiene molecule of pi bonding interaction between these 2 carbons, which accounts for its shorter length and the barrier to rotation. The valence bond picture of 1,3-butadiene, however, shows that the 2 pi bonds as being isolated from one another, with each pair of pi electrons stuck in its own pi bond. However, the molecular orbital theory predicts, and which is accurately, that the 4 pi electrons are to some extent delocalized or spread out over the whole system. It is this approach which is circumvented by using the hypothetical concept of resonance, because it is not possible to predict the nature of interaction of atomic orbitals to form bonding and antibonding MOs. Now, whatever diagrams I showed you, these are now theoretical diagrams. These are experimentally observed and then drawn. If experimental observation was something else, we would have drawn something else. So, molecular orbital theory is purely mathematical. It is totally based on experimental observations and then giving a theory to accommodate the experimental results. Therefore, whatever molecular orbitals we draw is based on what actually is present. Of course, the way I've drawn is probably not up to scale, but the fact of the matter is, in fact, I have not even given you the energy values, but the fact is that this is how the molecular orbitals exist. And it is very difficult to predict the molecular orbitals for certain molecules. Therefore, we use the concept of resonance, which circumvents the need to use a molecular orbital theory. So that's the end of this video, and I hope you were able to understand what I wanted to convey in this video. If required, please go and watch it again as many times as you want. So that will help you in understanding this particular lesson. If you have any doubts, any questions, any comments, any suggestions, any queries, anything that you want to talk about, please drop them in the comment section below. I am putting the link of all the previous videos in the description below. And in case you have not subscribed to my channel, I encourage you to subscribe to my channel. Consider subscribing. I make a variety of chemistry videos, and you can go and have a look at my playlist. I've made a complete set of videos on IUPAC nomenclature. I'm doing name reactions. I've done 2 lessons in physical chemistry, namely solid state and atomic structure. Of course, atomic structure I need to make one more video to complete it. But these are the lessons that I've covered so far, and I plan to cover as many lessons I can as soon as I can for grade 11th and 12th. So first of all, I'm going to talk about grade 11th and 12th, and then perhaps we might go for lower classes as well. But first, 11th and 12th is what we are going to complete, and that will take a lot of time. So with that, in case you do like the video, I would hope that you would hit the like button. And if you don't like the video, still hit the like button. This is Kalyan Kumar signing off. Have a great day. Goodbye. And thank you for watching.